Again, thanks for bearing with me through the setup. My name is Joel Molinari from Bridgewater Associates. We're investment manager in Connecticut. And what I'm here to talk to you about is how we are using R with some big data technologies on Amazon and semantic web technologies for knowledge capture and bringing these things together into this new platform we've been working on for the past 18 months or so. So one of the first things that we try to explain about what we're doing and why we're doing it is what is it that we do in data and data science. We work on trying to understand how the economic machine works, which means trying to use data and systematic processes to create sort of a compounded understanding over time of the causal relationships and why things happen in the economy. And one of the big things is that our business analysts, our domain specialists, are actually not very quantitative themselves from the standpoint of their engineering background. Very often they come from liberal arts training or other non-technical types of backgrounds, and we teach them how to use our tools and ecosystem. But really what we want to do with these platforms is enable higher order questions, so what we call goal-oriented research. Being able to, instead of the traditional ways that you interact with R and databases and connecting to tables and creating plots, be able to provide higher order applications that allow analysts to say things like, what do we know about deflationary cycles? And then have our ecosystem be able to assemble the visualizations, the data, the documents, and any other artifacts that we've produced over time related to this particular topic, and then also to be understand how that content was created. So really trying to focus on combining both the traditional things that people do in economic research, but overlaying this knowledge capture aspect and using some of these cloud environments for scaling. As you guys know, R has some limitations on in-memory capabilities, but as our earlier speaker said, that's just about finding the right tools in R that then can use things like Redshift or Spark or other big data types of compute layers. So some of the principles that we used when we were looking at developing this platform, we want it to be metadata driven. This is a very big factor. So we work against an ontology, how we think about our domain, which is the economy and data and visualization. And we really want the applications to be metadata driven so that they are semantically enabled and declarative in nature. We're focused on interoperability and loose coupling. I think everybody understands that concept. And we're using primarily open source tools, but we also blend in commercial stuff here and there as needed. One of the big topics, as I mentioned, self-service analytics. So we want folks to be able to use these tools in a bit of a higher order way than perhaps is typical. Some of the other stuff in here is relatively standard, but taking a look at our environment, and then we'll go into where R plays a role. We sort of have three layers, relatively traditional in that sense. We have our domain-specific applications, things like risk analysis or portfolio construction or idea generation in various forms, or search. We have a compute layer that includes both domain-specific operations, things like seasonal adjustments or time series operations. And we have general purpose operations, which are actually a big part of the process, which are things like data munging, ETL, and other types of work that are required to prepare the data sets for the domain-specific calculations. And then finally, underneath this, we have our storage layer, and that combines both the notion of curated data sets as well as less curated content, and in particular, metadata, master data, and the ontology around which everything is tied together. So how do we do this? This ecosystem has been in production for about 6 months on AWS. As we said, it's a Lambda architecture. Lambda architecture is a style of big data processing that was created by Nathan Mars, the author of Storm. And what we're doing is we're taking that, we're implementing with, again, a combination of tools, and then underlying all the tools is our ontology and our RDF stack, essentially that we're using in the tools to discover content, do data virtualization, metadata registration, and the like. So R, in particular, has a number of different roles. We're using R in our computation layer, we call the batch layer. And what we do is we actually attach R either to Redshift, which is a massively parallel columnar database from Amazon, similar to Vertica and some other offerings, or Spark. And then we actually program mostly in dplyr using other libraries like Zoo and the like, plus our own glue to stitch things together. So mostly we want folks to be working in a grammar that's agnostic to the compute layer. So whether you use Redshift or Spark or in memory or perhaps something else later, we really want that separation of concerns. The other thing we do is push the derived content from our processes into Redshift. That goes online into views that are exposed to a RESTful service. And then on the analytics side, we consume those again with either Shiny applications or Tableau or other types of endpoints that are consuming these structures. So this is what we've got from a technology and tool standpoint. And as I mentioned, one of the big factors, the thing that brings stuff together and what we think is really the permanent part of this ecosystem is the ontology, which is how we organize our concepts and how we organize the data and everything we build. And this is an example of our ontology, a certain part of it. And what you can see here, for example, the fact that we have a notion of geographic entities, which are divided into regions and countries. And then we have data, which we call measures, that can be either bilateral or unilateral, and we associate that data with geographic entities, things we call players, which can be governments or banks or things of that nature. And we also have other types of artifacts like wires, which are documents we write on a daily basis, and visualizations. And we attach those, for example, to a taxonomy of economic concepts that we've curated over time so that we can say, when we research something, it is about, for example, deflation in emerging markets, and then we can go and find that stuff. So the ontology evolves, there's properties for each of the things we think about, and that allows us to do a number of interesting use cases downstream in our tools, like provenance analysis. So provenance analysis is something very important to us because one of our principles is transparency and explicability of the data processes that we run. So the ability to understand where a value came from and what the relationship between the fields that produce that value are, as well as the operators that lead to it, is very important for our domain experts to be able to review the outputs coming out of our systematic processes and make sure they make sense, and that ultimately they tie to our overall understanding of how things work in the economy. So capturing provenance is a really big factor for us. Our semantic stack allows us to do this, and we're capturing it both from our ETL tools as well as R using or testing the R data tracker package that does provenance capture as for any script. One of the other examples that uses both Plotly in this case, as well as our metadata and semantic layers, allows us to do data virtualization and templatize visualizations. It's particularly important for us as we build up this knowledge base and we write a lot of research that the styles and the way that information is presented to our consumers is standard as best as possible. So what we do is we encode the styles and templates and layouts of how our visualization should look in the semantic layer, and then in R we draw from that to then render visualizations and have things like master data, what are the labels of the countries and the field names and the like available to us. The last thing I want to show you here is sort of more the interactive part, and I'll show you a Shiny application that is metadata driven. And what this application allows us to do in just about 300 lines of code is basically access data that's related to a particular part of our investment workflow, pull the data out of wherever it's stored. In this case, it's going to come from Amazon because it's on the cloud, but we also have internal databases. And then we're going to be doing some calculations on the data and master detail drill down. So what this shows us in this case is I want to look at what data comprises the income statement. And the application is pulling the taxonomy of the income statement out of the metadata repository. So we said the income statement is comprised of sales and operating income, and sales is comprised of cost of goods sold, et cetera. We are fetching the data and computing on it to create some simple aggregates. We're arranging in a different view how you might look at an income statement traditionally. And we're doing it across different countries, each of which also comes from our master data repository. And primarily, one of the use cases we do a lot of is aggregation analysis and then drill down. So in this case, we're looking at US companies and looking at their aggregate fundamentals. In particular, we'll say sales or net income. And what we might want to do is find out what happened in US companies in this particular period. So I can click on a point in my aggregation, and this is now going to locate what are the companies that are members trading in the US at that time. There's about 7,000 of them. And then we can say, for example, what's the company that had the largest change in net income? You can see Video Display Corp had a massive change in net income. This may be an outlier, maybe something that bears investigating. So these layouts are declarative and essentially based on the taxonomy of whatever it is that you're looking at in your economic domain. And the other thing that we're doing here is showing, for example, how we can then roll up the content into different groupings within which we classify companies. So a little bit small, but these are sectors across the economy, so financials and industrials and the like, the measurements of fundamentals, and the aggregations within each sector to these. And the last part here I can't show you because I'm not online, is how we can also integrate related documents that deal with the same topic that we had that we're working with. So these would be this would be a query against the documents that deal with equities and income statement analysis that we've written, and that again these things have been registered in our repository by way of an automated process. So we're bringing together a bunch of different things into one application, and if you take a look at ouch. You're right. And people fall off their chair when I speak. It's like totally I know it's a lot. So I just want to show you guys. Everything's okay? All right. So if you look at what the Shiny code looks like here, it's a small amount of code on the server side, and mostly what we're doing is we're invoking some functions to say, for example, if the concept I'm working with is the income statement, what are the related things that are part of that, and then go fetch them. And if you take a look at how we do this, behind each of these functions are Sparkle queries. These Sparkle queries are templates, and they essentially are querying the metadata database. So RDF, the RDF stack uses Sparkle as its query language. It's similar to SQL, but it allows you to traverse graphs. And so we can do things like, say, find the measures that relate to the income statement and all their child time series as well. Pull those out, get their URIs. The URIs are RESTful endpoints, and we can then just download that data, and we can have data frames either in the system or in Redshift where we could say, for example, have some data access functions, get a few measurements, for example, sales and cost of goods sold for the USA. We don't need to know where those things are, and they will then come back in a standard data model, which is tall data with certain dimensions that come out of our sort of core repository. So it's through this mechanism that we can both have applications that are interactive through the Shiny environment. We can also have widgets and tools within our ecosystem that allow us to have the same operations or data transformation or embedded visualizations in an interactive context as well. So let's see here. So we're early in the process of building this environment and really trying to understand how the content that we're producing should be captured and stored. That's one of the really big things that happens when you have 100 or more researchers using R all the time, creating tables and data and widgets, et cetera. You start to really lose track of where things are, and governance becomes a more and more important part of things. Just a couple more here on the specifics. As I mentioned, we're using Shiny, we're using Spark and Redshift for the compute layer, and then we're attaching via Semantic layer to different data sources that are both on cloud and on-prem, and doing it mostly through the R ecosystem on the front end side. Questions? Too much. Not enough. Not enough code. Not enough models. Yes.
Oh, so Redshift R, how do you are you calling, are you getting the data directly from Redshift? Or is there like an R language? There's no R language in Redshift.
So there's no R language in Redshift, but so you can interact with Redshift through dplyr. Let me see if we can, for example, so.
The native UGFs are kind of slow.
Yeah, the native that's right. Right. So mostly we use Redshift for functions that are expressible in SQL. There's a certain class of them, and for those we express them in dplyr. And for the functions that are not expressible in SQL, we either run them in Spark, or we extract them and we run them in a native library. For example, X13, we run in parallel just through R parallelization. But so there are limitations. There's definitely most of our domain-specific functions, like the seasonal adjustment or missing value imputation or forecasting, they don't actually run in Redshift. We either run them in Spark with Spark TS, or we pull them out and we slice them and then process them on a single machine. Yes, sir. Yeah. So the ontology allows us to. Let me see if I got a better example here. So this is the. Let's take a look here. So what the ontology allows us to, the ontology is essentially a schema for knowledge. So it's the same way that you have a schema in a relational database. It tells you the allowable properties of a table and the types. The ontology tells us what are the entities in our domain, what are their properties, and what are their relationships. So for example, one of the things we think about are geographies. And so the way we arrange geographies and the fact that we have a country and a region can contain a country, is what the ontology it tells you, and it allows you to enforce that in your applications. So you can both query a database and access things in a graph pattern, but you can also govern how your applications speak to each other, and the kinds of allowable properties and relationships between the classes in your world. Does that make sense? Okay. Yeah. I'm sorry, I missed that last part. It's from an organizational standpoint. Yeah, exactly. So you might say, if you are in the domain of retail, you have an entity in your ontology called the customer. You might have a buyer. You might have an account. A customer has an address, and then you might have a product. And then you can say that a customer buys a product. That would be a relationship in your ontology, and that essentially that structure then informs what data you can put into the database and then query against it. So then you can say, what products did this customer buy that another person also bought, for example? Yeah. Oh, Alteryx is great. We use it for ETL and data preparation. We also use it to, in some cases, launch our jobs. So when the data comes into our environment, it comes in the form of relational databases. Often it comes as files, mostly structured data. And Alteryx allows us to both blend, connect, merge, and transform the data so that it fits into our data model and goes into our immutable layer in S3. It also is used to do business logic on the data. So if we want to do certain summarizations or things of that nature, it just hooks up very well both to R, to Redshift, and then to tons of different data sources. And via its flow programming language, it has the secondary benefit of being able to, we can extract the provenance, the DAG, of how things are transformed without any interpretation. We just read it off, and then we can show the user, hey, these are the key steps that your job did when it transformed the data. Yes, sir. It's pretty recent. Yeah, we started it's basic. It's about I would say 12 months, 12 to 18 months, and growing. I would say now. So, yeah, we've had in general a bunch of different languages and tools in-house, not in-house, and so a lot of what we do though is loosely coupled. So while we have R, we also have folks programming in Scala against Spark. So interoperability is a very big thing. So R, we found, is very good, especially for our analysts and for our exploratory work. But we don't, for example, program our very hardened investment data signals with it because it's not type safe, and we can't quite get it as hardened as we like. So R has been, though, on the rise, especially with Shiny and the ability for folks to build analytics applications very quickly, tying into these sort of larger libraries that we're building as a platform team. It makes for a really fast iteration. Yeah. All right, thank you, guys.